Hi, welcome to the April 5th meeting of the CNCF IoT Edge Working Group. On the agenda today, we have a guest, Larry Peterson, who's CTO of the Open Networking Foundation and a very well-recognized name in software-defined networking, both in academics and industry. And one of the people here even indicated that he loved a book Larry has written on the subject. So without further ado, I'm going to turn it over to you, Larry, and you can talk about all things networking and Edge.
Sure. Happy. Thanks. And thanks for the invitation. So I have a few slides I thought I would go through. I don't want to take up the whole hour, maybe half of it, maybe not even that much. Kind of give you a sense of what we've been doing and where we see the opportunities, and then open it up for discussion and questions and whatnot, but also just feel free to jump in and interrupt me at any point. Let me go ahead and share my screen. All right, I'm going to hope you can see my slides.
Yeah, we can see them.
All good. Okay. Yeah, so what I'm going to talk about is a project that we've had at the Open Networking Foundation for the last 3+ years called Ether. One, it's private 5G. 2, it's an edge cloud. And 3, it builds on a lot of the SDN principles that ONF and before that ON Lab have been pushing forward for the last decade. In case you don't know ONF, ONF and ON Lab were were 2 organizations originally created about 10 years ago by Scott Shanker and Nick McEwen as the SDN initiative launched. As you probably know, Nicira was acquired, was a private company and was later acquired by VMware, but they wanted an open source variant to move forward to promote the ideas, and that's what ONF did the standards, OpenFlow originally, and Open Networking Lab was the software. The 2 merged, I don't know, 5 years ago, took the name ONF, but kept the open software mission. In any case, Ether is the latest project, and in some sense, it's kind of a capstone project of the last decade because it brings together all of these technologies in one platform. Okay, so now why can't I? Okay. All right, so what I wanted to do is just 5G has been at the core of what we've been, the transformation of 5G has been at the core of what we've been doing for the last little while. And it's my experience is it's kind of an unknown thing to a lot of people. If you grew up in the internet, you don't know a lot about the mobile network's internals. It's kind of parallel to everything that happened inside of the internet. And there's an important transformation happening now as we transition from 4G to 5G. And I wanted to give you a little quick summary of that because it really informs how we're approaching the edge. And so there's 2 big components. There's the base stations in 4G called eNodeBs, and there's the packet core, which is basically a fancy router. It has all the billing stuff that an ISP would have, but it's basically a router. In any case, it's closed. It's a telephony system, and certainly the base stations have been proprietary bundled systems. There's a software stack that runs there. The standard's open, but the software has not been for some time. So one of the big things happening in 5G is this is being disaggregated. Part of the stack moves out to the radio, part of the stack moves into a distributed unit, and part of it moves into a central unit. The gray here indicates it's D to A conversion and radio stuff that I'm not going to talk about. The blue is basically the data protocols, data plane layers, and the red is the control plane layer. The core, which is also bundled, has basically turned into a collection of microservices. So it's now called the next generation core. And the big takeaway from all of this, there's a lot of disaggregation happening and a lot of open software defined stuff happening. And now pretty much everything on the end-to-end path, perhaps save the amplifiers and the antennas and the DNA conversion at the edge, the very, very edge, are now open source. They're quite often cloud native, and they adhere to SDN principles. So that's the first big thing, and that's kind of what ONF has been promoting and trying to push forward. But my big takeaway is that the boundary between the access network and the cloud has now shifted. And it shifted basically over here. I guess you could argue that the radios are still kind of a transmission technology at the edge, but everything up from that is basically now open source and cloud native. And what ONF has been doing is promoting packages that correspond to those different components as open source. And so I want to kind of walk through those, and these are now going to be subsystems that are ONF open source projects. One more point before I get there. I did call out the SDN principle. Let me talk about that just a little bit more. It's not only disaggregation into cloud native, but we took the control component out of that stack and turned it into an SDN controller. And so now it's not local in an individual unit. It's now a global thing that controls a set of units. And I'm not showing it here, but there could be many central units. There could be many distributed units as they fan out to cover some geographic area. And certainly many radio units. And just like SDN in the wired network, there's a controller and there's a set of applications that run on top of it. They happen to be a little bit different than you might be familiar with. It's handover control, and there's still load balancing and link aggregation. Those are pretty familiar. Different radio management components and so on. I'm not going to jump into the details of those, but just to say that it looks a lot like what we might see in a data center as well, but now out at the very edge. There is still a management plane on top of that. If you work for a carrier, that's their OSS BSS system. But if you view this as now a cloud system, that's basically your management plane for your cloud. And also just call attention to, there's lots of control. Well, there's 3 basic control loops. There's a non-real-time control loop where you can change the policy. There's a near real-time control loop where you can make in sort of the sub 10 millisecond decision changes in configuration parameters. And then there's the real-time control loop that's basically the scheduler that schedules which little bits of data gets transmitted at any given time. And again, these are available as open source. There are some restrictions as you move out towards the edge. It's a little harder to get, there's less availability of open source software out in the distributed unit and that radio control scheduler, but it is still there. Okay, so the point here is that it's all disaggregated, it's all open source, it's all programmable. So the first project is called SD Core, and that's basically just a cloud native control plane. That is control. This is basically the component that runs in the core and controls, your mobility and tracking where you are and authentication and so on. And don't need to worry if you don't know the details of each one of these components, but it's literally a set of microservices. The standardization body, 3GPP, in my view, goes farther than they would need to in nailing down standard interfaces. These could have just evolved as you could have picked up a directory service, you could have picked up a NoSQL database, you could have picked up some standard authentication things and built this, but it wouldn't have necessarily complied to all the interfaces. So that's an aspect of this. That's sort of a legacy from the telephony days. There's actually also a 4G control plane in addition to the 5G control plane, and SD Core includes both. And right in the middle here is the data plane, or what the 3GPP folks call the user plane. But think of that as an IP router. It basically connects the RAN, which is the set of base stations, to the rest of the internet. And it's under the control either of a 4G or a 5G core. This collectively now is the SD Core project of ONF. And it's essentially a Helm chart defining the set of Docker images that you would want to deploy. The control, that was mostly the control plane. The user plane piece of it is interesting in its own right, and we have multiple implementations of it. We're building the switching fabric of our edge cloud out of programmable switches and smart NICs. So we have a variety of ways of building out the data plane. They are all P4 programmable. That just gives us a safe way of programming them. So there's a software path that goes all the way up into a server, and you can think of that as a microservice that's implementing the data path. Or there is another path that actually stays entirely mostly inside of the programmable switch, but occasionally has to go up to a smart NIC if it needs to buffer some data. So there's two implementations of the user plane function, the UPF, which is the data plane of the network. So that's SD core. SD-RAN is now a software-defined RAN, and that goes back to that controller that I showed you with the control apps running on top of it. We have an open source implementation of it that itself happens to be microservice based. So if you followed ONF and SDN for the last decade, you might be familiar with ONOS, the Open Network Operating System. That's been reconfigured from a set of components into what the telephony world calls the RIC, the RAN Intelligent Controller. That's that intermediate control loop piece that is near real time. And so it's built from a distributed store. There's a topology service that keeps track of everything out in the RAN that's sort of wired into the RAN, like where the base stations live. And then there's a device service that keeps track of where all the movable components are at the present time and their parameters. And then you can also configure it. So there is an organization called the ORAN Alliance, which is basically a little history here. The 3GP, apologies if I'm preaching to the choir here and you know all of this, but just real quickly, 3GPP is vendor dominated, and the carriers wanted to break vendor lock-in, and so they created the ORAN Alliance, and they is originally AT&T and China Mobile. And they set out to define some interfaces that would make it possible to buy the different components from different vendors. Long story short, there's an interface called E2 that is how this controller talks to the various elements. And the points I wanted to make here is all of this has been running. DT has been one of ONF's partners for a long time, and they set up a RAN field trial in Berlin. And all of these components here that I'm showing you have been running there. They're tearing it down now, but it's been there for quite a while. And there are some ORAN service models that have been defined that is supported by this software. So package this all up. This is a second component, the SD-RAN. There's just a picture of the Open RAN trial in a little bit more detail. I'm showing the SD core component with both the 5G and 4G core. I'm showing the RAN component, and there's some apps from different partners running above it. We've got a disaggregated split RAN with the CU and the DU and the RU separated. Radis, this has been a longtime partner. There's also a switching fabric, which I'll get to in a little bit, but remember I told you that the data plane of the 5G core was implemented in P4. Well, that's basically a switching fabric that's P4 programmable back in here. So Intel was certainly a partner, and all of this with Deutsche Telekom wrapping it all up. So SD core, SD fabric, which I'll talk a little bit more about in a minute, and SD-RAN are three software packages, open source projects of the ONF. All three are basically microservice based, so obvious relevance. So in a sense, what Ether is really an integration project to pull all those parts together. That's one way of thinking about it. So on the one hand, it exists by itself because there's a whole lot of management stuff that goes on. Another way of looking at it, though, is it's in some sense a little more than an integration of all those other pieces. So this is now getting closer to where I expect your activity is, which is what we are doing is building an edge cloud. And I'm giving you a little, a simple edge cloud here. And by the way, edge cloud could be multi-rack with a switching fabric, or it could be as small as a single server. And I'm showing you three servers here. It could have programmable switches, or it could have dumb switches. Those are all configuration parameters. But whatever that cluster, whatever the bill of materials for that cluster is, it runs the SD-RAN set of microservices, the SD core user plane set of services. That's the data path. And then whatever edge apps you want to run is other microservices. And this is all running on-prem, connected to a set of small cells, and then back central off-prem. And this could be literally in Google's cloud, which is where we run it in our deployment, but it could also be your enterprise's central cloud. That's where there are probably going to be some counterpart central apps we run the control plane of the core out here. The control plane could be co-located on the edge. It runs in either place. But the big thing I'm going to talk about next is basically the cloud management platform that turns those set of components into a managed cloud service in a very familiar way. But the importance of the way this is configured is that you have something called local breakout, which is to say communication between anything that's at the edge, your IoT devices, and the edge apps that are managing those devices in some way never leaves the premises, because the RAN and the core data path, data plane are all co-located on-prem. And this is something called local breakout. That has obvious performance value, latency, bandwidth, but also security value because you never go off-prem. Okay, so how do we build Ether? Hardware, it's all commodity. I'm going to show you smart switches, but these could be dumb switches as well. And a set of servers. These small cells are directly connected into the edge of that. Let's just say one of those switches or a couple of those switches. It's all Kubernetes managed. And I've got Kubernetes here, you should read the entire cloud native stack that goes there. It's Kubernetes, it's Helm, it's Fleet. We use Terraform. So that entire suite is actually running over here. And there's an OS that runs in all the switches, and then there's the network operating system that manages the fabric. So these dotted edges means this is the control plane for all of these switches, which is basically a standard, just like Google does it, and Microsoft does it in their networks, except it's all open source. The core user plane, again, that's the data plane piece, runs at the edge, and it can run as a microservice on the servers, or it can run as a P4 program in the switches. I'm kind of showing you both here. And the SD-RAN runs at the edges. And again, the SD core's control plane runs off premises unless you choose to configure it to be on this cluster. So that's the hardware and sort of the base level of software. And then we load workloads on it. I'm not showing any IoT Edge app workloads, but they would load on here as well. Then we call that the Ether connected edge. There can be multiple edges. And back in the central cloud is where we run multiple instances of the core control plane. And that's where the Ether management platform lives. We can call it AMP. So ACE at the edge and AMP managed by AMP. So what is AMP? AMP is an open source cloud management platform. It includes resource provisioning, lifecycle management, runtime control, monitoring, and logging. It has portals both for users, and think of a user maybe as the system admin at an edge who wants to set up new IoT devices, new 5G devices, whatever they may be, give different users different access, and an ops portal. If this is run as a managed service, then it's the Ether management team that would use the ops portal, but you could just download the software and run your own, and then you're also the operators. But it's important to distinguish between the users of the service and the operators of the service, and so we call those out here. I'm going to real quickly run through these four. Well, I'm going to run through three of the four. I'm not going to talk about resource provisioning. We use Terraform primarily there to go set up Kubernetes either in the cloud. We acquire a virtual Kubernetes cluster, or it's a physical cluster that we provision from scratch and bring it up so that you can then run it just as though it were provisioned. But let me go through the other ones. Lifecycle management is basically a continuous integration pipeline, and out of that comes an operational cloud. It's built entirely from open source. Many of these projects from the cloud native, from the Linux Foundation. I'm not going to go into the details, but again, Docker, Helm, Rancher, Terraform, and so on, Fleet are all components in here. The monitoring and logging component should be no surprise. We built that out of a set of open source components as well. And clearly you have to instrument the 5G components. So we've added the instrumentation, the dashboards and the panels and the collection machinery and the alarms and alerts that need to go off if something goes down. We've added all that specialization for the 5G case, but it's otherwise it's a pretty familiar tracking of CPU usage and bandwidth consumption and so on. The runtime control component is probably the most, in some sense, the most interesting because we had to do the most from scratch work there. And basically what it does is it gives you a programmatic API and a per enterprise portal so that you can manage the devices, you can aggregate the devices into groups, you can define slices to isolate traffic. Slices is basically the 5G way of saying a virtual network, if in a sense. You set the QoS parameters for slices. You can basically connect a set of devices to a set of application and then define the capacity or the parameters of the slice that they use to communicate. So this is all important because what it gives you is now an API that allows you to do closed loop control. So this runtime control is the piece I was just telling you about. And you can obviously read a lot of monitoring and data out of the monitoring side and then close the loop. I'll show you how we use that in a minute, but this is kind of the ultimate thing that we were after here. Just to give you a really simple example, one of the demos that we set up is video monitoring. And it's detecting motion. And as soon as it detects motion, it goes back to control through this control loop and turns up the bandwidth so that we can get higher resolution if there's some activity to monitor. So I've just really quickly talked about the open source components that build the management platform, and generating the control API is maybe the biggest intellectual contribution, if you will, to all of this. It's been deployed for some time, not huge number of sites, but more than 2 or 3, and you really have to start facing real operational concerns. And as I mentioned, one of those sites has been this first disaggregated 5G field trial, and that was done in collaboration with Deutsche Telekom. That's my overview of Ether, and I'm just going to take a few minutes now to talk about some of the research that our collaborators, Stanford, Princeton, and Cornell have been doing. This is a DARPA-funded project called Pronto. So Pronto funded the development work, the open source development work of Ether, and then the research to use Ether. And so basically we take an Ether cluster that just like the one that I've already shown you, and we instrument the switches, which are now they're Tofino switches, programmable with in-band network telemetry, so we can get fine-grained telemetry out of them. And we feed that back into a verifier that, because we program the data plane, we can verify that, in fact, what we're observing about the behavior of the data plane matches what we told it to do. And if there are any anomalies, because we're under various kinds of attacks and malware, then you can close loop control it and perhaps turn off a UE, turn off a base station, block this or that, or whatever the right remedy happens to be. We've connected that. Oh, and then I turned that green just to say that you can then reprogram as necessary. We have connected that in a flight lab at Stanford with drones that have 5G dongles on them. And so we're doing drone control. And so this particular research group had struggled controlling the drones with Wi-Fi, needed the guarantees of 5G. And so that's what we've done. And so there's motion capture. The cameras are wired in this particular configuration. The drone control is wireless. And then we subject this thing to all kinds of attacks. This was DARPA sponsored, and then we show, you attack in various ways. You can detect the attack and correct for it in real time. And so this is a demo that there's lots of videos of it that you can go watch and read more about. I'm not going to go into detail, but it's just kind of an example of how we've co-located the 5G Kubernetes workload with the edge application workload, taken advantage of the guarantees and stability of the 5G network in contrast to Wi-Fi to fly drones in formation. There's some research papers. There's some project, I'll leave this slide up. There's some project websites, both for Ether as a whole and for Pronto that used Ether. And those demo videos are available there. There's some background reading. I have collaborated with domain experts to write modest size, we call them microbooks. They're not terribly long, but they focus on, for example, the 5G case. This one is interesting in that there's an appendix that will give you a directory of all the software components I've been talking about and all the artifact repos where the Docker images live and where the Helm charts live and so on, and kind of steps you through the process of pulling those together to build an Ether for yourself. That's still a work in progress, but that's a source of information. So with that, let me stop, and I'll make these slides available, so I don't know that it's important to keep showing this particular slide, but let me just stop there and talk about, see if there's questions or comments or feedback or wherever you want to take this.
Thanks, Larry. That was great. If anybody's got anything, just jump in. I did log a couple that occurred to me as you were talking in the chat.
The runtime. Yeah, so not specifically, the AI ML is absolutely a lot of interest there. So the Pronto research team was not particularly AI motivated. They were mostly networking people. But Intel Labs has picked up Ether and has been doing various ML control demonstrations and so on. I can't tell you the specifics of them, but I do know that, well, they've got a, what's it called? OpenVINO, I believe, is an AI or an ML platform that they have. So the other sort of semi-related is I didn't speak a lot about what the edge apps were and kind of leave that to your imagination. But what tends to happen is you don't run an individual app, you run a platform that supports apps. So there's been work with an IoT platform and again, an ML platform and so on.
So it is, I don't know a lot about telephony, and I've had this long time confusion with sort of where is 5G going? Why is it really so exciting? Like I see cell networks as sort of an extension of the, OCI 7 layers, right? And now it just reaches out a little bit further into a mobile device that uses a radio network instead of a Wi-Fi network. It seems like there's more here. Like, could I take this Aether and put it into 1,000 retail stores and create a private network?
Yeah, that's exactly what's happening. And the way I characterize it is this used to be the domain of telcos and their very, very small set of incumbent vendors. And I have no idea who's on the phone here, but you can imagine who those three vendors are. And it's been a very tight relationship, and it's been a very closed system. What has happened as a consequence of segregation and opening and so on is now you've got cloud companies interested in doing exactly that. And not just cloud companies, but Walmarts and the like. Don't take them specifically, but companies like that, Target and so on, that are building private networks. So now the question is, why 5G versus Wi-Fi? Because you could build exactly that with Wi-Fi. And that's still a little bit of an open question, but what our experience seems to be is you can get more reliable jitter behavior, basically. that you don't get the variation in latencies that you do with Wi-Fi. And if you're trying to fly a drone, that jitter can cause it to crash. Now, is it, retail, is it quite the same thing? It's hard to say. It's the outdoor nature also, it just tends to do better. I know there's agriculture pilots, smart ag. Yeah, so it all boils down to is our situation. So step one, make the mobile network look more like a cloud. That's happened and is happening. Step two, can you find use cases that really take advantage of 5G versus Wi-Fi? And there are a few of those that I think are out there. It's not about your cell phone. It's entirely about smart retail, smart ag, and so on.
Right, right. Yeah, I mean, I see, so a factory having a private cloud, especially with the ability to run controllers. A lot of the things I've done with cloud native at the edge has to do with controlling the tiny edge where I can't put Kubernetes, but I want to control some robotic arm or something like that. And so I maybe run workloads in Kubernetes, but they need to be wired to these things. So it is definitely an interesting use case for that.
Well, I think you put your finger at another issue here, which is a lot of this stuff is wired right now. The factory arm is wired. Those real-time devices are quite often wired.
Yeah.
So there's an element of build it and they will come going on here.
Okay.
You see the advantage of wireless. You see the advantage of the reliable latency, predictable latency. But in terms of where those two meet, the devices aren't there. The use cases aren't, they're just starting to emerge. So whether that'll take root, it's still a bit early.
Yeah. And that I guess leads to my other question about general purpose compute. Is there an expectation that this will provide general purpose compute in the way a cloud currently
Absolutely.
does?
Yeah. With the exception of the first workload that you load on it is the 5G workload. It's otherwise looks just like any other Kubernetes cloud. And you can, like I said, you quite often are ready to, you start deploying it with a single box, but this will scale up to a multi-rack instantiation if you wanted it to. Mm-hmm. We're not talking warehouse, hyperscaler size necessarily, obviously, but yeah.
So to follow up on Mark's questioning, it just hit me. I'm curious as to whether the 5G part of this is sort of an isolatable plugin where you could swap in a different radio technology. You did mention Wi-Fi, but you could see LoRa for longer range, possibly. And inside of a factory, maybe you could use Bluetooth Low Energy or some other wireless, and as well as whether this thing would support something like a service mesh to integrate wireless plus hardwired into one centrally control planed managed connection fabric.
Yeah. So hiding the specifics of the wire, the transmission technology is a good goal. It's very challenging in the sense of how overwhelmingly prescriptive the mobile network's architecture is. Just a little editorializing, the mobile network, 4G, 5G, 3G, it wasn't a fixed, there was too tight of coupling of the architecture and the technology. Every time the technology changed, which of course it was going to, the architecture had to change. Contrast that with the internet where the architecture stayed relatively fixed and the technology just kept plugging in. As a consequence, you have to go up pretty high to unify that. Service mesh might be the right layer. There have been attempts to unify Wi-Fi and 5G. There is another control plane you probably have heard of called Magma that abstracted the wireless control plane and then controlled both Wi-Fi and it was 4G, didn't get to 5G. That's definitely where we'll eventually end up, but we're a ways from there right now, that being very easy. I mean, in my view, the very fact that the 5G control plane core, I often just say control plane because the user plane comes out of it really easy. The control plane of the core, now being microservice based, sets us on a vector that will eventually morph into something reasonable. It was originally very prescriptive as to exactly what those are. But when you discover, you know what, I could change this and no one needs to be the wiser because I was never trying to support my IoT device, calling a random IoT device on the other side of the world. That now being in motion, eventually these things will unify, but it'll take time.
It seems like even within the telco space, eventually, unless they're planning to go out of business, there has to be a 6G, right? So, this mission of making it plug-in and abstractable seems like a natural, unless you wanted to deem this a learning experiment that you throw away when you move on to the next thing.
So the 6G is really interesting. My view of it is that we won't care about 6G because it'll just be, now that it's cloud native, it'll just be a natural iteration of that. And there was, well, I mean, first of all, 5G, 6G are marketing terms, there's a sequence of standards that progress over time. And there are boundary conditions that you need to have the standards at. You would like any radio to talk to any core. But internal to all of that, those interfaces were overprescribed. So what's 6G? I don't know. It can now be, because we're now on cloud feature velocity timescales instead of telco vendor timescales. These things could morph very fast. And then who's to say where the line's drawn? The radio technology will probably change, and that'll be a perfectly good reason to call it 6G. But the rest of it, I don't think it's going to be as relevant.
I think there's another challenge to this, which is cost, and that, like, the cost of pushing data through a cell network is exponentially more expensive than using the wireless or Wi-Fi, the wired networks that we have today, even though they're ultimately going through the same system eventually. I feel like it's not economical to use 5G right now. As long as you're, if you're using somebody else's cell towers, as soon as you connect to a cell tower, if you make your own little private network and you don't go outside very often, that's fine.
Well, I think that's the exactly point. So you're probably right about the macro cell that AT&T and Verizon run. I don't know. I wouldn't know how to predict the future there, but I think it's the private version of it that is the economics are going to change. You don't have to have AT&T or whoever manage it anymore. You could literally manage it yourself, or you get your favorite cloud company to manage it for you. And so those costs are going to change, and I would think, migrate towards the mean here and not be that much more expensive than Wi-Fi, hopefully with additional ability to control.
In terms of putting on the equivalent of your own private cell network or things and looking at your demo involving drones, I assume that drones maybe were endpoints connecting to this, but how much of the radio control is baked into the idea that these cell towers, if you will, are fixed locations like they would be in the legacy world, versus an idea of, if I'm doing a private network, what if I deemed that trucks in my fleet are actually acting as mobile moving cell towers, maybe drones as well, that you could locate demand-based, or just count on the fact that you have delivery trucks in metro areas at such a density that you don't have to rent real estate for them. What if you made the truck fleet the cell tower network and counted on them being dispersed?
Yeah, well, so yes and no. I love that idea. The challenge is going to be, we still have the problem of the spectrum and the radio spectrum. And so, this is now a national issue. So in the US, we have CBRS, and it is not as unlicensed as Wi-Fi is right now. And I don't know if you know the history of this spectrum. It's actually, quote unquote, borrowed from the Navy, and the Navy could call it back at any moment. So one of the challenges right now is when you bring up a private 5G small cell, which you could put in a truck with the processor that runs the software, and you could drive it around, at least on your, you could certainly drive it around on your premises if you had the rights to that, the spectrum there. That's it. So this is an important part of this whole, how does this play out? Because the spectrum is subdivided, and I can't remember I never remember the acronyms, but part of it, you can turn your small cell on and just use it. It's like Wi-Fi, except with the caveat that the Navy could call it back at any moment. So you literally have to check in with a central database to see if it's okay to keep using it, if you're following the law, if the FCC law. Then there's a band, another sub-band of CBRS that you can go acquire the rights to, and a lot of sites / enterprises have done that. But also, so has Verizon and AT&T. And so now, from a university setting as an example, did my university go get the rights to that band on their campus? Yes or no? There are not very many that did. Some did, anticipating being able to use it. And one way you can use it, by the way, is to put up cell service and then sell it back to the carriers, but that's a whole nother ballgame.
Yeah, hey there. Yeah, so I know, like, just I guess it's probably really agreed that there's several areas that's very exciting. Cybersecurity, edge computing, and AI. So I just wonder, in like going forward, what can be done together between the ONF community and the CNCF Kubernetes community? What kind of topics that can be looked at? So going forward, just for any new business and the technology and opportunities.
Yeah, I think the underappreciated, and there's a question like this here, does AMP manage infrastructure as well as workloads? And the answer is yes. The management of all of this is in many respects, the hard problem. And what's going on is we're trying to morph how the network is managed from being managed in telco style to being managed in cloud style. And as you do that, then you start adopting more of the cloud native tools. And so that's the high level point. Down one level from that, I think the control API, everyone understands what it means to offer, pick your favorite, storage as a service. You know how to go to Amazon and acquire, what is it, Dynamo or whatever, and you know what, you get an API and you now can control storage and you can build apps on that. The counterpart for the community is basically connectivity as a service. We don't have connectivity as a service. We go and acquire connectivity from a carrier historically, but we get virtually no control over it. Now we're given, this notion of an API that lets you read dials on what it's doing and how it's being used, and then turn knobs on it and what knobs are available. That API is, I think, extremely fertile ground for I don't know what, for figuring out how to coalesce around it. And it is going to be a very powerful interface, very important interface. So, I mean, beyond that, there are a few specific things about managing small cells that are a unique kind of device, a little bit. And how do you, let me see if I can take an example. I know how to deploy Kubernetes on, I know how to set up the infrastructure for Kubernetes on commodity servers. I know how to deploy workloads on the Kubernetes I've set up as infrastructure. How to do the same kind of thing with small cells and the user devices is another ballgame that I don't, there might be opportunities there. It is
small cells, do you
much
mean-
harder. It's much harder to set up a small cell than it is to set up a Wi-Fi access point right now.
By small cells, are you talking about something that would be hosted on very limited compute resource? Like maybe it couldn't even run as a Kubernetes cluster? Is that what you mean?
The small cell, shoot. Well, I got one right next door, but it's basically, think of it, it looks just like a Wi-Fi access port, an access point.
So maybe even too small to run Linux or something getting.
You don't
that
get to
small,
run
or-
any, well, the ones that are commercially available, you don't run anything on them. They're basically like connecting an AP into your server.
Okay.
Could be
So all
like
of
a,
the stuff I'm talking about is running on the server that you connect your AP into, or your small cell into.
that could be like a camera, right? Or a CCTV camera. That those could be small cells, right?
Say that again?
Could be like a video camera or a CCTV camera.
No, so the video camera or the IoT device or your cell phone or whatever, your drone, I use the term dongle because we literally plug them into Raspberry Pis and that gives you a thing. Those are UEs, that's the term, user equipment.
Okay. No, Kubernetes provides a platform, right? Like a device drivers that can be identified. Like I think there is a project called Akri that uses it, right?
Well, so the devices that connect to this, so the small cell is the radio, with just a little bit of software on it that is just bundled with the radio.
Okay.
So the devices are certainly, that's an entire range. You break into my Android, you can do whatever you want. It could be a Raspberry Pi running Linux. There you can do whatever you want.
Yeah.
So can the small cells be commodity hardware, or do they have special hardware?
That's a great question. And the answer is there are software-defined radios.
Mhm.
So you're still going to have some A to D components in there. And once that thing blows up into a macro cell that you find out in your along the highway, the amplifiers in there are highly specialized, and that's hard to break that vendor lock in. But on the femto cells, sometimes they're called that. They're basically like Wi-Fi access points. Those can be built out of commodity hardware and be programmable. There's I don't know the specifics of it, but there's a project at Intel called FlexRAN. And it's basically open source with the stipulation that the code has to run on an Intel processor. But it's basically that bottom layer of the radio, of what could be a small cell. But when I use the word small cell, essentially what I'm saying is it implies that it's using the millimeter wave spectrum, which has limited reach, so it's not appropriate for a macro cell.
So, but does Ether control plane manage what gets deployed to those small cells then?
No.
Oh.
Those it could, if that were in fact programmable, then that would be an aspect of it. But in most of what I was talking about, the control of all of that sits back on a commodity server running Linux as a Kubernetes workload. So we run the control of it. You connect the radio to the control. We do still have to provide a data path to get to it, which is like the functionality of an IP router plus, because it has to track it has some mobility aspects to it.
And kind of going off of that, so you're mentioning how these small cells have a shorter range, and so you need a server that's running Kubernetes, have that control plane near it. What does it look like in the when you're setting all this up to say, hey, this node that's near this small cell, this is your small cell. What does it look like to connect that small cell to the management node near it?
Oh, so the management node and the small cell are over a fixed, it's an overlay network over a fixed infrastructure. So you might just literally you could run it over your Wi-Fi, or maybe you wanted more predictability, so you run it over something else. Yeah, it basically the small cells connect to each other, in effect, and back to the centralized control point as an overlay over some wired network. So now it depends on what wired network you prefer in your enterprise.
So is there already some sort of a mesh networking component to connect up the small cells?
Yes, it is. If you were going to deploy this on a campus,
yeah,
corporate or academic, whatever, you would probably run it over your local wired packet switch network, your local Ethernet.
mm-hmm.
I got a quick question. So the use cases. So can we apply this architecture for connected cars, like autonomous driving?
So interesting. Yeah, yes, you could. Cars go much further, and so are going to connect to the macro cells. As you go down the highway. The private enterprise version of this is which we're mostly focused on is going to be in some limited physical location. The second you're in your car, you probably have the option of going longer distance. And now you're going to be connected to your carrier's 5G network. And while this technology could be adopted by the carriers, they're moving very, very slowly in that direction because they're still depending on the incumbent vendors providing them with all their hardware.
Yeah, actually, I was talking about like a restricted area for autonomous driving. Yeah.
I mean, in principle, this gets back to the truck idea. You could actually run the whole network in the vehicle itself.
Yeah.
Or pull the compute components back into the geographic area's central location, and then connect through the distributed set of small cells.
Thank you.
Can I ask a question? Hi guys, sorry I just landed a bit late to the meeting, but Larry, one quick question. I come from telecommunications background, and I've had some lectures in my master study where it said that most of the workloads that generally tend to happen on femtocells and everything, are they still like functional programming stuff? Like there were some lectures where Elixir is generally used as a, let's say, on the femtocells to just transfer that particular data packet to a certain structure or something. Am I still wrong, or is that still the trend that goes on, or have femtocells evolved quite drastically?
Well, no. So the femtocells, aka small cells, are while they can be software-defined radio, and there are open versions of them, they are currently bundled devices that have their own internal protocol stack. That stack, as I'm trying to explain, is shrinking, and more of that is becoming open, and actually more of it is centralized. So what actually runs in each individual radio is less and less. But there is still software there.
Okay.
And it just, there's the lowest level of control loop is every millisecond approximately on that order. I have to make a decision as to which little bit of data to transmit on what frequency. And that decision is very much a real-time decision, and that will continue to run on the radio unit, as it's now called.
I see. Thanks.
One thing I've been learning about the overall landscape for CNCF, Kubernetes, and networking. One thing I find is whenever we talk about networking in the CNCF Kubernetes world, mostly it stops at the service mesh layer. basically the underlay network is not discussed. So that's reasonable because that's the way it is, and you usually don't need to worry about that. However, it would be great to have a clear understanding of the landscape and how the overlay and underlay work together, and how it's going to affect the edge computing.
Yeah, I think that's really putting your thumb on the key issue here. And that, if you remember that early slide where I said the access network edge has moved, that is the important, it is one takeaway, that's what it ought to be, because now everything to the right of that looks just like any other, I'm going to say literally Kubernetes workload. It's microservice, it's open source, it's cloud native, and so on. And the only thing that is now outside of that and sort of beyond our reach or concern is literally the radio piece, the radio unit. And as soon as that happens, and we're in the midst of that happening, everything about operational practices, everything about feature velocity comes into play. And as a consequence, because there's turmoil there's opportunity. Because it's not the old ways of doing it just are not going to apply anymore.
Yeah, I agree. The telecom industry really is up for disruption. It's very exciting at the same time. It's just there's a lot to digest to understand what's going on there, what kind of opportunities are out there.
Yeah, I completely agree. I'll just type it just because. If you go to that URL, you will find a description of 5G written by someone who, until he started to try to understand it, had no clue. It was just a pile of acronyms and some obscure information theory math. Basically, this describes, from my perspective, how it's being transformed into something that looks very, very familiar, and will come, and as a consequence, will start to change, because it's now it's an entirely new world. It's the cloud world, not the telco world.
Larry, did you share a URL? I don't see one in the chat.
Same here.
Oh, I'm sorry.
Yeah,
I'm sorry. I didn't. Sorry. I got into a not a to everyone. Sorry.
I just put it in the meeting notes too.
Thank you.
Hey, Larry, I'm curious about this being an open source project, of what the health is in terms of who's contributing to it. Is it a mix of telco vendors plus telcos plus users, or what is the mix? And if someone was real interested, how would they get on board? Maybe first determining whether they're interested and then contributing. So
this URL, 5gsystemspros.org, includes a description of the software and some pointers. So I'll just leave it with that one, where you go find more information. The reason, so this has been an interesting journey in the sense that who writes network software? It is not the consumers of the software. It's not the telcos. It has historically been their vendors. ONF, funded by the telcos, ONF set out to build an open source software-defined substrate that would break the vendor lock-in on behalf of the telcos. That, in a slightly twisted way, is exactly what's happened over the last 10 years. But what ended up happening is that we also wrote software that was now more cloud-friendly than it was telco-friendly, and therefore anyone that understands the cloud can now do that. So who's our participants? We've been in the business of disrupting first the vendors, so no, they did not help us do it. We're now in the business of disrupting the carriers, so no, they originally funded us, but they really didn't have the engineering staff. The work was all done by ONF engineers to a first approximation. That's not to say there weren't many contributors, but it wouldn't have happened without the ONF engineers. 1 year ago today, those ONF engineers got acquired by Intel. So today, most of the software coming back into these projects is coming from Intel.
You know, that's real interesting to hear of that, because I've read some fascinating articles on this too, and it could be that some of the disruptions that people here posed as questions, like taking this in new directions of using even non-5G radios, are really interesting. But it sounds like maybe people would have to contribute labor to use these abstractions to make that happen. But maybe there's a way to put together an organization to bring together the people interested to work together on that in the typical open source fashion.
Yeah, and over the past year, ONF has transitioned from being an engineering organization to being a community organization, just like LF, right? There are companies that are taking the software and they're building product out of it. They don't generally contribute back in quite the same way as you would like. Intel's certainly still contributing in a big way. We're finding a lot of exploratory organizations that really aren't in the space using it to come up to speed, and they're contributing some back. Some of those are universities or like-minded affiliated things. Government entities, DARPA, NIST, is another place that is interested in seeing a lot of activity here. So it's whoever wants to see movement here that's causing it to happen, that's now contributing.
So if you have community meetings for this kind of brainstorming discussion of where could we go on this, I'd like to hear the links to those, or provide them and we'll put them in the notes later.
Yeah,
or you're welcome to even use this group for that if such a thing hasn't existed up to date.
So I'm just chatting, I'm just getting it noted in here. So Tuesday we just changed our time, 9 a.m. PT is the Ether TST. And yeah.
Okay, we're a little past the top of the hour. So how about if we have last call for any parting questions or last remarks?
Yeah, I agree. It would be interesting to get our hands on small cells and play around with this. I think that's where you're going, Larry. Steve, with yeah.
That's, I mean, getting your hands on the plane,
right? I can get hobbyist use. I can get a Raspberry Pi. I want to connect it to one of these small cells or multiple and play with it.
Yeah. So today, 5G small cells are still a little expensive and a little bit hard to come by. 4G is easier, and you basically get the same setup. It's just some radio details that change. Raspberry Pi with a dongle and a server. That's exactly what I've got in the next room, and that's my sandbox for playing with this. I've got a 5G small cell too, but it's a bear to get working.
Thank you.
Well, thank you, Larry. That was a fantastic presentation. We'd invite you to come back again for a refresh if you're interested. In terms of logistics, the next meeting is going to be postponed and slipped by a week because it conflicts with KubeCon. And we speculate that a number of people who normally come to these are going to be physically at KubeCon in a different time zone where this meeting time just doesn't work out. So let me look up. The next meeting is going to be on the 26th of April. We have one item on the agenda now, which is the Edge Native white paper supplemental assets with 5 names listed there. And that's only going to take a portion of the meeting. So if anybody wants to add something else, as usual practice for this group, members are welcome to add their own agenda items. Just list it with an estimated time and go for it. With that said, I'll publish the recording. It usually takes a week or 2 for the logistics, but thanks for coming, everybody, and we'll see you next time, or we'll see you physically at KubeCon for some of you. Bye.
Bye.